said, I will be presenting Theano, and rather than, it's a bit different than the other keynote speech because I'm focusing on a specific package, but I think it will be useful to pretty much everybody who works with numbers. So it's still widespread. So let's start. As I said, when you work with numbers in Python, you usually start with a Python script that manages some data, reads and does stuff. But as you run it, most of the time, if you have a large amount of data, you start to think that, well, it's too slow and you need to speed it up. There are easy approaches that you can use with Numba and NumExpression. Numba is sort of a JIT compiler. It's kind of a successor to Psycho. Maybe you've known that, but now that Psycho is unmaintained. Numba works sort of the same. It doesn't work exactly the same, actually. But you can decorate certain functions in your program, and it will compile those into assembly code to run faster. Of course, it has limitations. It can't optimize everything. NumExpression is more focused on optimizing series of operation on NumPy arrays. And well, if that's what you do, it's quite fast at what it does. But even with those tools, sometimes it's not fast enough. So you need to get some other tools. And Cython is very popular to either annotate your code so that it can compile to C code and go faster, or just wrap around an existing C library and use it to perform your core computations. But if you have even more data, even that's not enough. So you might have to go into multiprocessing or threading. Well, threading in Python is sometimes less useful because you have the global interpreter lock, which prevents multiple threads from executing in parallel while manipulating Python objects. Multiprocessing sort of alleviates this problem by using multiple processes to work on all of the processor cores, but you have the overhead of transferring data back and forth between processes, which can be very costly if you have to share a big amount of data. And even if those are not enough, then you can try to use GPUs to go much faster. There are two main well-known packages, PyOpenCL and PyCUDA, which give you the full access to the CUDA or OpenCL API. However, you mostly have to write your own GPU code in order to use that, and it requires quite a bit of knowledge. And also, at the end, if you've modified your script incrementally, adding all these things, it can kind of resemble a big pile of stuff that's not too organized and hard to maintain. This is where Theano comes in. We provide an API to define you define your computation as a graph, a virtual graph, and then you just tell Theano to compile it, and it can use the CPU, it can use the GPU, it can do all of that pretty much automatically for you. Of course, it's not as fast as a hand-optimized program, but it can get pretty close. And this is useful if you need speed, but you don't have the huge resources to engineer something that's really efficient for your use case. Like if you have a small team, you're doing research or trying out prototypes. Oops. OK, so the goals of Theano are, first, integration with NumPy, because NumPy is the format for numerical data in Python. Any package which deals with numerical data goes through NumPy arrays at some point. We also want to enable transparent use of a GPU. That means you don't have to rewrite all of your program or most of it just to use a GPU. You just change a flag when you call your Python on your program and tell it to use, I want to use the GPU, and it should work. It's not exactly 100% there yet. You have some small things you have to pay attention to as of now, but it's mostly there. One of the other thing that's also a goal, and that's the part about defining a computational graph, it's that we can do differentiation on the graph or other manipulation, which are hard to do if you only work with numeric data. I'll get into a bit more detail about that later. Also, working with the computation graph enables us to do some optimization on the way computations are performed to get more speed or to get a more stable version of the computations, because sometimes certain expressions will behave unstably around certain values, and we can rewrite these expressions into a different form that is stable. And finally, we also perform dynamic C code generation either for the CPU or the GPU once all of the optimizations are done, so because we kind of need C to get speed. So let's jump into a little example that should show you a bit how Theano works. This is a really, really tiny and simple Theano program to compute the sum of squares of something, of two values, and I'll go through it line by line. So the first is import Theano, which should be sort of familiar. It's a Python package, and to use it, you have to import it. Now, these two lines define variables. These are Theano variables, which are not exactly the same as Python variables. These variables have a type, and they have a dimension. In this case, we are building scalars, which represent a single value, and the type is not explicit. I didn't specify an explicit type here, so it defaults to float64 or double. The string here is a name for those variables because it can be easier when you name your variables to find them after that in a graph, but it's not mandatory. And this line defines the expression. At this point, there are no computations performed, meaning in any way, A and B, the variables we defined before, do not have a value associated with them. They are symbols. They're placeholder, if you wish. And this creates a new variable, C, which is a placeholder for this expression. All intermediate steps of the computation in Theano are valid variables and can be reused to build further operations. In this case, it's doing the square of A plus the square of B and square root, which is sum of squares. Now, at this point, C defines a structure that resembles something like this. So you have the two inputs. The green box at the top are the inputs to the graph. To the left, there's B. And to the right, there's A. In the middle, there's something else. It's a variable we didn't define, but that's actually a constant. It corresponds to the 2 value in the power. And it's there only one time because Theano recognized that we use the same value twice, and it doesn't need 2 different variables because it's the same thing, and it's a constant. And between the pink circle things are element-wise operations, which means that they apply to all of the elements in our variables. In this case, our variables are scalars, so they only have one element, but we could have defined vectors or matrices and worked on all the elements of those. So there's a power on each side, and then those two are added, and then there's a square root, and then the blue box at the end represents the output. This isn't optimized or anything. It's just the raw representation. After that, once we have our graph computation in the form of C, we need to compile it. And we do this by calling Theano.function. We pass in a list first that contains all of the inputs of our graph in the order we want to pass them. And after that, we pass the expressions we want to compute. And here I only pass one expression, but you could also pass a list to return more than one value. So it can compute more than one thing at the same time. And this returns a Python object, which is callable and acts like a function. And at this point, we can call that with values and get a result. Also, after Theano, when that function ran, the graph is optimized to this. So we only have two inputs now, A and B, because it inlined the power of 2 into a SQR operation, which is square. And it collapsed all of the operations together. This is important because it allows to reduce memory traffic. So you don't need to read and write as much as you would if you separate all of these operations. And this allows you to go a bit faster. And finally, as you can see, the object, you can call it with 1 and 2, which gives us back the square root of 3. The array here is because the scalar type is also a NumPy type of 0 dimensions, so it gives us something like that, which is, it acts like a double anyway, if you need to convert it. Now, I'll go into a bit more detail about certain types of graph transformation that we do and explain how they work. So here is another example. This time we work with matrices and vectors. So the big X is a matrix we create. It means a variable of 2 dimensions. And it's also all float 64 because we didn't specify an explicit type once again. So, and Y and Z are vectors here. What I compute in out is the dot product of X and Y times a scalar constant, here 0.6, plus Z times 0.4. Some of you might recognize this from BLAS as a GEMV. But we don't call a special GEMV function or anything like that. It's just a regular dot product and multiplications and additions, and it doesn't need for, yeah. And then we can compile it with the function call as before. So the graph as defined by out looks something like this. So all the operations are there. The green things at the top are all inputs. There are 3 X, Y, and Z variables, plus the 2 scalar multipliers. So this gives us 5 input, and then we have dot product and the multiplications and the addition and the output. This doesn't look efficient, but after optimization, it recognized that this pattern is actually a GEMV operation and collapse all of that together into a single call, which will call into the BLAS library and be optimized as usual. This is the sort of thing we can do for to get more speed out of your program. And one of the nice things of working with a graph representation like this is that this set of operations doesn't have to be in the same module. So if you use a library of Theano expressions made by somebody that has part of that operation, and then you use your own code that you add, let's say the dot product times a scalar is in some library, and then you, in your code, add a vector plus a scale, times a scalar to that expression, it will recognize that across modules, files, or anything like that. Because it doesn't look at the source code itself, it only looks at this graph, which doesn't know from where it comes. So the other type of optimization we do are for stability. And once again, it can do that across files. In this case, the operation is on a scalar. It's the exponent plus, logarithm of exponent plus 1, which is also known as log1p. This operation is unstable near, I don't remember the value, but it's unstable near 0, I think. And this is the regular graph before optimization. After optimization, we collapse all of that in the middle to a single soft plus operation, which is a more stable version of that optimization, that expression. that will not have a instability problem around the problem value. Okay. Now I'll get into a slightly bigger example. Yeah, in this example, I introduce a new type of variable also. So you can see there's a matrix and a vector. Here they are F matrix and F vector. This is because I want these to be float 32 or just float. So these are typed as float 32 or just float. I'll get back to why in a moment. And after that, there's Theano that's shared that you can see here. This defines what we call a shared variable, but could be also understood as a global variable in a program. It allows you to specify a numeric value that will be shared between multiple Theano functions. This is sometimes useful if you have a statistical model or a learning model or something like that, and you can place the parameters of that model in a shared variable, and then you can derive from that variable two expressions, one for training and one for testing, and they share the same value. Also, a shared variable enables you to change its value inside of a function. I'll get back to it after. Okay, so here we define an expression with our variables. It's the sigmoid of a dot product, which is the logistic regression. And then we define a cost, the energy over that operation, which is the y times log 1 minus y times log of 1 minus mu. And sum all of that and take the negative over that. So, and that's our cost, if you wish, for training the logistic regression model, which use w, the small w, as a parameter. Now, normally to train this sort of thing, you either derive the gradient manually on a sheet or with some program, or you devise some other form of training. But here I give an example with gradient descent, and I just call t.grad, which is a method from Theano.tensor, and I say my cost is e, and the parameter I want to maximize over that is w. And this will give GW, which is an expression of the gradient of the gradient of E with regards to W. And this is possible across this sort of manipulation is possible across almost all Theano operations. So you'd never need to write a manual gradient. If you need to do some really fancy manipulation because you don't want a regular gradient, it's also possible to get a gradient from one point to the other and then do some custom manipulation and then the gradient from that point and onward. I didn't do that because it's a bit more code and it wouldn't fit in the slide. So after getting the gradient, we create a function with two inputs, x, which are the data points here, and y, which are the label to predict with the logistic regression model. I don't specify any outputs here, so it won't return a value, but I specify is a keyword parameter called updates, which is a list of two element tuples. The first element has to be a shared variable, and the second element is an expression, which can be anything. And the value of the shared variable specified in the first element will be updated to the value of the expression at the end of the function call. This kind of thing is useful, especially if you work with other devices than the CPU. Because if you would just work on the CPU, you could just return that value and set it manually inside the shared variable. But if you work on a GPU, for example, doing it this way can help you avoid the transferring your data back to the CPU to return. And then once again, back to the GPU to set it into the variable. The way in updates, if the shared variable is on the GPU, it will automatically transfer that without going through a transfer to the CPU. Okay. So let's look a bit at the graphs here. So this is the graph of E here. Yes. So this is the graph of E, our cost. As you can see, it's a bit complex. There's the dot product and sigmoid in the top left, and all of the rest is to compute the products of mu and y, and 1 minus mu and 1 minus y, with a couple. And at the end, there's the sum and minus negation sign. Okay. And once we compile that expression, it would give us a graph like this, which, as you can see, it replaced some part of the graph by a GEMV, and that's the dot product at the top. And it also merged all of the other element-wise operation in a single pink rounding, and then it does the sum over that, and then the negation, because it can't do it before the sum. There are also blue and orange bubbles. The blue bubble is a special type that gets the shape of an input, and this is required for the orange bubble, which is a allocation, so it allocates some data for the GEMV to work on. Yeah, okay. This graph is the gradient expression from the GW equals t dot grad E comma W line. It doesn't look very pretty because we use a naive algorithm to get the gradient. However, we can do this and still get good performance because we compile the operation after, which will declutter that graph a lot. So as you can see, this is the same gradient operation, but after compilation, there are two GEMVs now because there were two dots before, one at the beginning and one at the end. And it collapsed most of the element-wise operation that it could together in two pink blocks. And I think there's the sum somewhere if it needs it. Okay, so now I've mentioned the GPU a couple of times, and the GPU can be really useful, even if you don't do a lot of effort. As I said, it's almost transparent to use GPU with Theano. So the first thing you have to pay attention to is that our current GPU backend only supports float32 numbers or floats. So you have to define your variables as float32, which is why I use F matrix at the top here. That's kind of the only detail you really need to pay attention to. You can also use the t.matrix version, and there's a configuration flag in Theano which allows you to switch the type that's used for that generic constructor. So you can set it to float32 and then use the GPU. So this is a small program that performs a simple dot product between two matrices to get an idea of how much speed up a GPU can give on a sort of really simple problem and unoptimized, because the inputs here on the CPU, so it needs to do the transfer, then the multiplication and transfer back. But even then, you'll see it's faster. So this is how you run it on a CPU. I don't have the fastest CPU on the planet, but it's something, it's a time to consider. And then if you want to run it on the GPU, the only change is that you specify an environment variable called Theano flags, and then you set device equals GPU 0. Well, this could be GPU 1 or 2 if you have more than one GPU on your machine, but I don't, so GPU 0. And then it prints an additional line saying using GPU device 0 and the name of the device. Here, my card is not one of the best, but still, it's about 10 times faster for a small, unoptimized program. And this includes the transfer time back and forth. So as you can see, using a GPU can really, really pay off, because as you're doing more and more computation between the input and the output, all of that avoids transfers if it's all done inside of Theano. So it can go much faster. You can get a much better speed up than that. We've seen some programs going as much as 140 times faster by using a GPU. Yeah, and also, I don't have slides, but this, because I thought about adding it this morning, actually. So one of the things about Theano that's really nice is that you can use it for pretty much any sort of data that's numerical, even though in our laboratory, we mainly use it for machine learning. It recently passed a sort of milestone for us, if you could say, because we had a trouble in the past that every 5 years or so, we would somebody would get bored with whatever tools we would have to run stuff and develop a new paradigm. And this would entail basically reinventing the wheel every 5 years, so we didn't progress as much in our tools as we could, because there would always be something new to re-implement everything in. However, Theano has been with us for about 8 years, and in that time it has endured. There was a first attempt at a library on top of Theano specific to machine learning, because that's what we do. And eventually, of course, as always, people got bored with that library and started a new one. But the new one also uses Theano, so we don't lose all of the effort we made. And to me, actually, this proves that Theano can be a really good basis for implementation, because it doesn't enforce a certain model in your application, it just performs the computation. And on that note, I also know that PyMC uses Theano for a statistics stuff, and there are a wealth of libraries already using Theano also. So I encourage you to look into this and start using Theano in your project if you're doing computations with data, numerical data. So, are there any questions?
A few questions. You mentioned that you were doing machine learning, and that's how Theano development started, right?
Yes.
Is it? Do you have other examples of other areas or other domains where it's used?
I do know that one physics lab somewhere is using Theano for some of their simulations. And I know people in statistics are using it, as I've said, PyMC, and a Monte Carlo package also uses Theano.
Okay. Is the learning curve hard, or?
It depends. Some people have trouble shifting from numerical thinking to symbolic thinking, and this is required to efficiently use Theano. But apart from that, it's not that hard. And also, one of the nice things is that writing a new operation for Theano is not extremely complex. It's a bit more work than just using it, but it's readily doable. And actually, if you're interested in Theano, I just forgot to mention that. This Monday, during the sprint session, we'll be doing a tutorial on using Theano, which is going to be a bit longer than this.
Thanks.
Yes?
Yes. When you are doing all this vector analysis in the Theano, how is your stencil defined in space?
What analysis?
All those vector calculus?
Vector.
Yeah,
Okay.
that vector analysis, all those calculus involving gradients and spatial derivatives.
Yeah. The gradient is it doesn't consider any special space. It's an element by element gradient. It could be, because it's It doesn't do vector gradient. The cost in the grad method has to be a scalar variable. So it doesn't perform a differential operator, actually. It could be doable, but we didn't write it because we don't need it.
Hi. Does Theano have any competitor exist?
In machine learning specifically, I know there's Torch, which is a Lua package. I know also, well, you could say Caffe, but it's a C library to do deep learning and vision, but it's more targeted toward vision, and Theano is a bit more general. And there are probably others, but actually no, all the other libraries I know in machine learning are based on Theano. So.
Okay, thanks. But do you recommend or suggestion for what condition we should use Theano and what condition we should not?
In which conditions should you use Theano? Is that the question?
Yeah, it's another question.
Okay. Theano is good at dealing, currently it's good at dealing with large data, meaning matrices, vectors of a certain number of elements. If you only deal with scalars, it's good, but it could be improved a bit because there's a bit of overhead in starting a function and things like that. So if you don't do if you do a really tiny amount of computation inside the Theano function, this could not get as fast as it could be. However, if you're dealing with somewhat large data, it's really good for pretty much any application.
Thank you.
Is there anyone still has questions?
I have two questions. First of them is that does it support the multi-GPU? And the second one is why it only support the floating 32 instead of support for floating 32 and 64?
I'll answer the second question first because I didn't really understand the first. So we actually have two backends in Theano, and the one we call the old backend, which only supports float 32, and the other one which we inventively call the new backend, which actually supports all of the integer type from int 8 to int 64, and float 16, float 32, and float 64. But this backend is not complete yet because it's missing a lot of our operations, our basic operations. So this is why we don't promote it as much. It's in the works, and it will be completed soonish, I think, I hope. But if you are interested in working with float 64 data or things like that on the GPU, you can look at that backend, and maybe it will help you. Also, we didn't push as much for float 64 on GPUs because we mostly use CUDA GPUs, and frankly, the performance in float 64 sucks compared to float 32. Added to that, for what we do, we don't really need the extra precision, so it's kind of a trade-off where it's slower and we don't need it, so we didn't put too much effort. The new backend, however, does support it.
So are there any very good bioinformatics-related application of the Theano? Like, can you name some of them so that, yeah.
What do you mean, applications of Theano?
Like, in bioinformatics field.
I'm sorry, I didn't understand the word.
Bioinformatics, so using Theano for maybe biology or medical-related analysis. Are there like maybe projects that are based on Theano?
As far as I know, there was one project about analyzing MRI data with Theano. And we might have a project about analyzing patient data with Theano in the future, but that's the only two I know about. There may be others, but I don't know everything.
Okay, I have a question. I have used Theano, so I think the most secret part, magical part of Theano is a Theano function is the updating mechanism. And I want to ask if some bad use case will slow down the updating mechanism or
You mean sample use of the updates mechanism?
Yeah, if anyone is there some bad usage?
Some bad usage?
Bad usage case will slow down the updating mechanism?
Bad use case for updates.
Yeah.
I don't really think there are, unless you don't need I mean, if you're, well, you could make something bad, but it would be forced. I mean,
Okay.
if you really have a value that you need to change as a function is called, it's kind of the best thing. If you only use this to communicate between different process or I don't know, something like that, then maybe it could slow down the computation. But as far as I know, it doesn't have any negative impacts unless you really need, well, if you need access to the value, you can still get it from the shared variable, but it would be faster to return the value from the function if you need it. So maybe if you use it as a buffer for a return value, that's not optimal. Otherwise,
hi, thanks for the great talk. So I have one related question. So if I'd like to implement some reinforcement learning algorithm, and the environment is implemented in a CPU side, and the agent is running in the GPU side, I think the traffic is kind of the problem. So do you recommend to implement everything, including environment and agent, in the GPU? Or is there any good way to implement this kind of framework which need interaction between agents, which learns, like has the parameters,
yeah.
and the like environments?
We had plans, well, we have plans since a large number of years to implement asynchronous transfers inside of a Theano function. It was never really realized because it has never been a major bottleneck for our use case. However, I do know that some people did reinforcement learning on the GPU with Theano. I'm just not really familiar with how they did it exactly.
Okay, I see.
It's possible to do loops in Theano if that's what you need for the reinforcement learning algorithm. So it could be possible to do both operations on the GPU.
On the GPU side.
And avoid transfers this way. Yeah.
I see. Okay, thanks, yeah.
Okay, any question?
Could you further comment about how you do profiling with Theano?
There is a built-in profiler which can help you find which operation is the slowest in your graph. And we mostly use this to know which operation we should speed up or where we should concentrate our work. Otherwise, it takes a bit of experience if you have a Theano function that's slow and you don't know why. You might have to look at the graph to see like, oh, are there a lot of CPU, GPU transfers? Because that's usually the case. If you're working on CPU only, then you can try to see like where most of the time is spent. And usually if you get a profile and like 95% of your time is spent doing a gem operation, you probably can't go much faster than that.
I have one more question. Because a lot of people ask me this question. They want to ask you, is there some schedule or timeline Theano will support OpenCL?
Yes, the new backends that I've mentioned, which support for more types, also support OpenCL. However, that's even less complete than the CUDA portion, because most of the apps don't have, they have CUDA kernels, but not OpenCL kernels. We haven't written them because all of our hardware is NVIDIA. However, we do welcome contributions if anybody's interested. We will try to work on it a bit, but I mean, development in our lab is mostly centered on our priorities, but we welcome external contributions, and we do have a bunch of external contributors which push their what they need.
So is there some easier way or step or tutorial can new developer join the Theano project?
We do have a bit of tutorials online if you want to learn how to write operations, how to add C code to a next operation you have, or things like that. It's all in the Theano documentation. As for new developer, we welcome pull requests on GitHub from anybody. So you don't need special credentials or anything. If you have written code that could fit into Theano, send a pull request, we'll review it, and that's it.
Okay, any question? No? Let's thank Arnaud again.